Let me start with two everyday experiments that feel almost the same, but hide a real difference. First, toss a fair coin twice. Second, roll a fair six-sided die just once. On the coin, the first landing heads and the second landing heads can perfectly well happen together. On the die, even and odd on that single roll can never both happen. One outcome, one parity. Those are two completely different ideas. One is about whether events can share an outcome. We'll call that mutually exclusive. The other is about whether one event changes the odds of the other. That's independence. They sound alike, and yet, for ordinary events, they almost never travel together. Before we separate them, three small pieces of language, all about a single experiment. The sample space, capital S, is just the set of every possible outcome of one trial. An event is any subset of that sample space, a bundle of outcomes we care about. Event A, the number is even, is the set 2, 4, 6. Event B, greater than 4, is just 5 and 6, and its probability, P of A, is a number between 0 and 1. For fair, equally likely outcomes, it's simply favorable outcomes over total outcomes. To set symbols carry the whole story. A cap B, the intersection, means both A and B occur. A cup B, the union, means A or B or both. And one more. The conditional probability of a given B is the chance of both, divided by the chance of B. It answers, once I know B happened, how likely is A? Hold on to that. It's the key that unlocks independence. Start with mutually exclusive, also called disjoint. Two events are mutually exclusive when they simply cannot both happen in the same trial. Picture them as two circles that never touch because they don't overlap. There is no shared outcome at all. In symbols, a cap B is the empty set, and so the probability of both happening is exactly zero, a clean side effect. When nothing is shared, the chance of A or B is just their two probabilities added together. Nothing to subtract, because nothing was double counted. Independence is a different animal entirely. Two events are independent when learning that one happened tells you nothing new about the other. The odds simply don't budge, written with conditional probability. It says the chance of a given B is just the plain chance of a knowing B changes, nothing. Rearrange that, and it turns into the form you'll actually compute with. The probability of both equals the product of the two separate probabilities. And notice what that picture is telling you. Independent events usually do overlap. There sits their shared region, the violet lens. Overlap is not the enemy of independence. The product rule is, let's set them right next to each other, because the pictures make the difference obvious. On the left, mutually exclusive. Two circles apart, no overlap. So the probability of both is zero. On the right, independent. The circles overlap, there is a shared lens, and the size of that lens is pinned down exactly by the product of the two probabilities. One idea is about sharing an outcome. The other is about influence. Keep those two questions apart, and you will never confuse the terms again. Here is the twist that surprises almost everyone. For ordinary events, ones with real, positive probability, these two properties actually push against each other. Watch what happens if we demand both at once, mutually exclusive forces. The probability of both down to zero. But independence forces that very same probability to equal the product of the two. Set them equal, and the product of the two probabilities is forced to be zero. And a product is zero only when one of its factors is zero. So at least one event had to have probability zero all along. So the verdict is sharp. If both events genuinely have positive probability, they cannot be mutually exclusive and independent at the same time. It's one or the other. In fact, it flips your intuition completely. To disjoint events with real probability aren't unrelated at all. They are strongly dependent. Because the instant one of them happens, the other becomes impossible. Let's make this concrete. Draw a single card from a standard 52 card deck. Let A be the card is a king and B the card is a heart. Are these two mutually exclusive, independent, both, or neither? First, the three probabilities. There are four kings, so P of A is 4 over 52, which is 1/13th. There are 13 hearts, so P of B is 13 over 52, 1/4. And their intersection? Exactly one card is both a king and a heart. The king of hearts. So the probability of both is 1 over 52. Now test it. The intersection is 1/52nd, which is not 0. So they are not mutually exclusive. A card can be both. For independence, multiply the two probabilities. 1/13 times 1/4 is 1 over 52, which is exactly the probability of both. The product rule holds, so king and heart are independent. And the conditional view confirms the intuition. Given the card is a heart, the chance it's a king is 1 in 13, the same as with no information at all. Learning the suit told you nothing about the rank. Now a case that goes the other way. Roll a fair die once. Let A be even, the set 2, 4, 6, and B be odd, the set 1, 3, 5. Each has probability 1/2. No number is both even and odd, so their intersection is empty, and the probability of both is 0. That's the very definition. They are mutually exclusive. But are they independent? The product of their probabilities is 1/2 times 1/2, a quarter. Yet the probability of both is 0. 0 is not a quarter. The product rule fails, so they are not independent. The conditional view makes the dependence vivid. On its own, odd has probability 1/2. But the moment you know the roll came up even, the chance of odd crashes to 0. Knowing one told you everything about the other. That is dependence at its most extreme. Your turn. Roll a fair die once. Let A be at most 3, 1, 2, 3, and B be even 2, 4, 6. Are they mutually exclusive, independent, both, or neither? Pause here and work it through before I do. Here's the walkthrough. Both A and B hold 3 of the 6 faces, so each has probability 1/2. Their intersection is the single face 2. It's the only number that is both at most 3 and even. So the probability of both is 1/6. Test exclusivity first. The intersection is 1/6, which is not 0. So they are not mutually exclusive. The face 2 lives in both. Now independence. The product of the probabilities is a quarter, but the actual probability of both is 1/6. A sixth is not a quarter, so the product rule fails. They are not independent either. So the honest answer is neither. Not mutually exclusive and not independent. If you reasoned your way to that, you have truly understood the difference. Because most real pairs of events are exactly this. Neither. Trap 1. Assuming mutually exclusive means independent. It's the opposite. Two disjoint events with positive probability are dependent. One happening makes the other impossible. Trap 2. Assuming independent events can't overlap. They usually do. Independence only demands that the overlap equal the product of the probabilities, not that it vanish. Trap 3. Assuming different trials are automatically independent. To coin tosses, yes. But to draws from a bag without replacement are dependent. The first draw changes what's left. Always check the definition. Let's lock it in. Mutually exclusive means the events can't share an outcome. Their intersection is empty, and the probability of both is 0. Independent means one event doesn't shift the other's odds. The probability of both is the product of the two probabilities. And whenever both events have positive probability, they cannot be both at once. It's one or the other. Remember the three anchors. Even versus odd is exclusive and dependent. King versus heart is independent and overlapping. And most pairs you meet are simply neither.